All right, welcome. We think of computers as these perfect calculating machines, right? They just follow instructions. But how do you teach a machine to think, to solve a puzzle where there isn't one clear path, but a whole maze of possibilities? Well, today, we're diving into exactly that. How AI makes smart guesses to turn problems that seem impossible into something it can actually solve.
So, let's start with this. It's a classic 8 puzzle. The goal is super simple. Just slide the tiles around to get them in order, 1 through 8. But here's the real question. How would you solve this in the fewest possible moves? Seriously, take a second. You wouldn't just start sliding tiles at random, would you? Nah, you'd have a strategy, a gut feeling about which move is best.
Okay, now let's picture a computer trying to solve this, but without any of our human intuition. We just tell it the basic rule. You can slide a tile into the empty space. How's it going to tackle the problem? Well, it would get lost, and fast. It's like sending it into a maze completely blindfolded. We call this an uninformed or blind search.
And what a blind search does is pretty mind-numbing. It looks at the puzzle and generates every single possible next move. Then, from each of those new states, it generates all the possible moves after that, and on and on and on. It's literally trying to escape a maze by mapping out every single path, one by one, with absolutely no sense of direction.
For our little 8 puzzle, this brute force approach gets out of hand really fast. There are over 181,000 unique ways these tiles can be arranged. Now sure, a modern computer could probably chew through that, but remember, this is a tiny, simple puzzle. What happens when things get just a little more complicated?
For problems that are even slightly more complex, this brute force method doesn't just get slow, it fails. It fails spectacularly. The number of possibilities just explodes, and the super powerful computer we rely on, well, it grinds to a complete and total halt.
And here is that problem of scale in black and white. Look at these numbers. A search that's just a few moves deeper, what we call depth, doesn't just take a bit longer. It jumps from about 2 weeks of compute time to 350 years. And you need a petabyte of memory. No way. Brute force is just not going to cut it. So clearly, this isn't how we do it. We don't take centuries to solve a puzzle. We've got a trick up our sleeve. So there has to be a smarter way to teach a computer to do what we do, right?
Yes, there is. And that smarter way comes from basically copying our own secret weapon. We don't wander through every random path. We have an incredible advantage: intuition. Think about it. When you glance at that scrambled puzzle, you instantly see which tiles are totally out of place. You focus on moves that look like they're making progress. You're making an educated guess, a rule of thumb that helps you cut to the chase and lets you ignore thousands of moves that are obviously a waste of time.
And in the world of artificial intelligence, this powerful idea of an educated guess has a proper name. It's called a heuristic, and it is the absolute key to making search algorithms truly smart.
So a heuristic function, you'll often see it written as h of n or h of n, is basically how we give that human-like intuition to an AI. It looks at the current situation, like our scrambled puzzle, and it gives it a score. It gives it an estimate of how close it is to the finish line. Now, it doesn't know the actual answer, but it makes a really good guess.
Okay, to make this really clear, let's look at 2 totally different ways we could design a heuristic for our 8 puzzle. Each one is going to give the AI a slightly different kind of intuition. All right, our first heuristic, let's call it H1, is super simple. It just counts how many tiles are in the wrong spot. In our example here, every tile is misplaced. So H1 gives a score of 8. But our second one, H2, is much smarter. It uses what's called the Manhattan distance. For each tile, it counts the number of squares it has to move up, down, left, or right to get home. When you add all those up, you get a score of 18. Both are just guesses, but you can see that H2 is a way more informed guess. Now, the really good heuristics have this special property. They are admissible. And all that means is that they're optimistic. An admissible heuristic might guess less than the true cost to solve the puzzle, but it will never, ever overestimate it. And that's critical because it ensures the AI doesn't get scared away from what might actually be the best path.
So we've got this powerful new tool, this educated guess. How do we actually put it to work? Well, we use it to turbocharge our search.
And we do that by plugging it into one of the most famous, most effective search algorithms in all of AI, A-star search. A-star is pretty much the gold standard for finding the best path from A to B, and it gets all of its power directly from a heuristic.
And the formula for A-star is just beautiful. For any spot on the search path, it calculates a score, f of n, and that score is just two things added together. G of n, which is the actual cost of the path you've already taken to get here, plus h of n, which is your heuristics estimated cost to get to the finish line. Then, A-star just explores the path with the lowest total score. It's constantly balancing the cost so far with the estimated cost to go.
And here's what that looks like in practice. A blind search just looks at the cost so far. So it can easily get tricked into going down a path that seems cheap at first, but turns into a long, costly dead end. But A-star, with its heuristic, is way smarter. It looks at the total estimated cost, so it can intelligently focus its energy only on the paths that seem genuinely promising, saving a massive amount of wasted effort.
And the real magic here is a concept called pruning. It's incredible. Because the heuristic gives the algorithm a sense of direction, A-star can confidently just ignore huge parts of the search. It can prune away entire branches of possibilities without ever looking at them, because it knows they're probably just long scenic routes or dead ends.
And the results are just dramatic. Let's go back to our A puzzle. A blind search has to explore a huge number of options, but when we use A-star with our simple misplaced tiles heuristic, that number drops significantly. And when we use A-star with our smarter Manhattan distance heuristic, the search becomes a tiny, tiny fraction of the original. It's that simple. A better guess, a better heuristic, means a radically more efficient search.
So, okay, this is cool for puzzles, but why does any of this really matter to you? Well, because this exact idea isn't just in a lab. It's running inside technology you use every single day.
Ever wonder how your GPS or Maps app finds the fastest route so quickly? It's not checking every road on Earth. It's using a heuristic to estimate travel time and prune the bad options. When an enemy in a video game cleverly navigates a whole map to find you, that's A-star with a heuristic. From robots figuring out how to move around a room to how data gets routed across the internet, heuristics are what make these incredibly complex problems solvable in the real world.
So here's the big takeaway. Heuristics are the engine of practical problem solving for AI. They make a crucial trade-off. They give up an absolute perfect certainty in exchange for speed and efficiency. And that trade-off allows them to find fantastic, or at least good enough solutions to problems so hard that a perfect brute force answer would literally take longer than a human lifetime.
And that leaves us with a really interesting final thought. If a key part of what we consider intelligence, both in us and in our machines, is the ability to make a good guess, to take a smart shortcut, and to let go of the need for a perfect answer, what does that say about our own search for perfection in such a complex world?